asked a question for part C. I don't like. I was kind of like that one was like I didn't know because sometimes like it's some of the practice problems I like you can solve that in place. So that's what I did. But I also like when you look up what the input resistance is, but I don't know if it's talking about a different resistance. Like I thought like that resistance going into the terminals. Not like I just it's subtracted.
I'll see if I can.
That's what it's yeah, I got like 1.25. Yeah, that's what he does. For like that's what I had for each like yeah, that's what I
Okay, we have attendance 1955. It's the code.
but it's usually there.
Yes. What happened?
Doesn't look like it's available for us.
It's not.
Weird. There's this like the signals goes one or whatever.
Oh no.
Yeah.
Put in another class. Okay, I will fix it. Thank you. Shit.
Oh, that's why you're talking about the Did they ever talk about Australia? I feel like it's forgotten. It's just up there. I mean, I'm sure it's in the heavens. I mean, you could talk about. But it didn't really matter. It's just not what's interesting. Yeah, exactly. We're gonna put all of the worst people on Earth on this island. Yeah, but then it's like wouldn't happen on an island that's got a million challenges. European and we'll go that. And some of that's we don't have any out there. Really? It doesn't do the well, I guess we'll have like European exploration. Why was Eastern Europe? It's not Eastern Europe. Why was Western Europe and like Eastern Europe?
Okay, check it now. Sorry.
That's an amazing point, actually.
Okay. Oof. Oof. Okay. So let's get started. Next week, this time we have first midterm inside the class. Is lockdown browser. I can make a test before exam, similar to questions. What else? The questions mostly we have about 15 multiple choice questions and 6 or 5 essay question. You need to enter answers in a inside, but it's all based off Canvas. That's it. But today, what we're gonna do today is still we are in instruction set. We're gonna talk about RISC-V instruction set. Today we're gonna talk about logical and conditional. So last class we talked about load and store. Load and stores are important because the only instructions that working with memory. Working with memory is a little tricky because you need to access the address, and memory is a byte addressable, but registers are 8 bytes, so it's a little tricky how we load or store. So we explain this is the memory, and this is bytes. And to access that, you need base and offset. So for example, you can use load instruction, load double word, and put it in X5, for example, is the destination. The offset can be 8 bytes. This is byte. And a base is, for example, X20. So X20 is inside X20 is the address that's pointing one of the, this byte. And you add 8 to that to get the destination. And when you load it, you are loading 8 bytes from that part. So for example, if this is 1, 2, 3, all the way to 8, you are loading this part. If here, for example, is 0, 1, X, not X, I mean, for example, F0, A2, and whatever, it's gonna go here. Little endian, remember? Little endian. The shortest address gonna go to the least significant bit, and go all the way. So that was something that we explained last class, A2 and more. What we're gonna do today, we're gonna have another example. We wanna see how we can access arrays using assembly language. Just example, and then go to actually logical operations. Logical operations are good for manipulating registers. Sometimes register is 64, but you want to access one of the bytes or some of the bits even. How we can do that using this logical operation like AND or XOR and shift left, shift right. And we're going to talk about conditional operation too, how we can implement if and else or loop in assembly language. So we're going to talk about that if we get the chance. So last week, we talked about these 3 group of instructions: register format, R format, register format, that just working with registers. They they have this structure. So this is for register format. The structure is like that. All instructions are 32 bits, we know. Why all the same? Because we want to be regular. Regularity makes simplicity, and simplicity makes them to can, do a step of running instructions very similar, and that helps us to do it with pipeline. So that's why regularity is important in RISC computers. 32-bit, all instructions 32-bit. So they start with opcode showing which instruction is that, what is doing. Like for example, this opcode is for add, and this opcode is for subtract, but they are similar. So, but we also have those functions, function 3-bit and function 7-bit, that these two also helping opcode to see, for example, this is one showing this is a subtract, not add. So these functions help still to opcode. The other group of instructions that we talked last week was immediate instructions when we have constant numbers. Immediate instructions can be with, like most of instruction, if you put an I at the end, like add I, subtract I, and I, or I, makes them immediate. So when you are working with constant numbers, you can do that. For immediate addresses, we have still opcode. We have register destination and register source, but the rest, that is 12 bits, considered as a constant. Load also has the same format. That's why we consider load also in this immediate format, because exactly the same format. So the format is like that. For example, in load, you have opcode, you have register destination, you have a function that helping opcode, and this register source, that this register source is actually in load is just base address, and this offset is the constant number that's showing offset. So you are adding base with offset to find which information you want to load from memory. Okay, we also talk about a store type or S type. A store has a different format, because in a store we are actually storing into memory, so the destination is memory. So we use these 5 bits that use as a source register as a part of the address, and register 1 and register 2. Register 1 is source S1, and register 2 is base for the address that you want to write in memory, and these two addresses together makes offset. Okay, so we explained that as well. So this was just a recap from what we had last class. Today, before starting other parts, we're going to have example of array. Arrays are important and complex, of course. But this is simple array because it's constant. This number is constant. It can be variable too. We can see how. But in this case, is easy. A8 and A12, both are constant. So it's a little simple. So what we need to consider is that we need to have some assumptions. Assumptions showing which variable assigned to which register. Sometimes we call that binding. Binding, we bind that. So we consider, for example, H, register X21, because these variables are just not assigning to the real place. So we need to assign them to a real place in the computer. So H, we consider that, for example, X21. So the compiler doing this stuff. That's why when compiler is smart, can optimize better and makes the faster code. So compiler is important in that case to do this assignment, this binding. So we consider a variable H assigned to register X21 and a variable A that is an array assigned to X22. And what else we need to know? We need to know the array is how size is elements of array. In this example, we consider array double word. We're gonna make it simple, same size as registers. So the size of array is 8 bytes. So this is the array. Let's consider array A. A is base of this array, and each of these is 8 bytes. So that's the array. But this is not physical. This is just actually data structure that you are using. But we need to assign this in a memory. We want to see how this is assigning to the memory. So we have A as the address, X22. Here we have bytes. X22, when I do a parenthesis here, showing the address of that, not number of X22, address is there. So that's pointing that point, but we want A8. So what we need to do, we need to find offsets for A8 and A12. So how we do that, because each of elements actually are 8 bytes, so we need to multiply them together. So the offset for A8 is number 64, and for A12 is 96 bytes. So it means, so this is for, if this is 1, for example, this is 64. This is showing A, this is showing A, this is A8, and this is 96, showing A12. Okay, so we find these two offset. So the rest is just coding. First, we load 64, X20 is a base, X22 is a base with offset 64. This is gonna make A8. We are adding this, we are loading this first in one temporary register like X5, and then we are adding X5 with H, that is X21, and put the result in again temporary register like X5. We add that. Oh, and then we right now we load that. Now we need to store it in A12. So we store it, store double word SD, Okay, I don't know why it's not writing this side. Okay, SD. We are storing X5 into memory. Which memory? A12. A12 has 96 as an offset and X22 as a base. So if we run this code, it's gonna copy A8, add A8 with H and copy that in A12. Any question about that? So that was all constant. So the array, we knew 8 and 12. What about if it's not constant? Like, for example, you are accessing a I, for example. How we can access this? In this case, any idea? How we use like a variable as an index for array? Yes.
You multiply I by 8.
Yeah, of course. Great. Yes, you just need to multiply I by whatever you want. For example, here you can, because multiplying by 8 is like, we need to shift it, of course. You need to shift it to do multiplication. But to access that, in that case, you need to consider, for example, 0x, whatever that you put as I, like x10, for example. This is I. Okay, we're gonna see that in example soon. But let's clear this. Okay, so imagine we are trying to access AI. So, and I is x22 and A is x20. Okay, let's make this x22 to be similar to that, and this is x21. Okay, in this case, so what we need to do, because each element of A is 8 word, so to find the index, you need to multiply x21 by 8. How to do that? We can shift it. We're going to see the shift instruction, but you already used them in your assignment. So you do shift left, logical, immediate, x21, and put the result in x21, 3 bits. When you shift it left, it's multiplied by 8. 3 bits, 2 power 3 is 8. So is multiplied by 8. Like what we did here, we are do that automatically with shifting left. And right now you need to add to the base. You're adding, for example, x21 and x22, and put it again in x21. So right now, x21 is AI. So whatever we did here, with numbers, here you did with registers to find this I. We imagine that x21 is I. Do you get that? Any question about that? I think you had in your assignment as well. Yes, so you kind of familiar to that. Okay, so that was something that we wanted to cover before going to next part. So that's a cleaner version of the previous example. What we're going to see that a lot. Okay, so logical operations. Logical operations are simple operations, mostly bit by bit, or sometimes in level of bytes. Like, for example, you want to take 1 byte out of word or double word, we can use combination of shifting and or XOR, whatever you had in digital logic, you can do with these operations here. So what type of operation we can do? So we can categorize logical instructions to bitwise logic, like bit by bit, like AND or XOR. So AND or XORs, they can be immediate as well. So you can have AND I or I or X or I when you have immediate. If they are not immediate, They are just doing with registers. So for example, you are ANDing x21 with x20 and put the result in x5. So what is doing, whatever is in x1, okay, whatever is in x1, each of this is 1 byte. And this is x21, this is x, I don't know, it's 2020. We AND them together and put the result in x5. So, and we know the AND is kind of masking. Masking means you can just let part of the array go or some part not go. For example, if you AND x21 with 0, 0, f, 0, 0, 0, f, 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 because you are ANDing that, the 0 going to make this part 0 and just pass this part of the x21. So this is called masking. Masking can be used a lot. So whatever is here, this part going to move to this, and this 2 bytes going to get 0. This is x. This is actually each of these two consider 1 byte because it's hex. Okay, so that was something that we can do. So this is bitwise. Let's clean this up. We also can do shift operations. Shift operations also very important. We saw application of that in multiplication and division too. Shift left is like multiplication. Shift right is addition. When we are shifting left or right, we are entering 0 the other side. So this is important. When we are adding, when we are shifting, we fill it up with 0, the rest. That's important. We also can have shift arithmetic because we can have logical shift or arithmetic. In arithmetic, we are keeping the sign. If we are shifting, for example, right or left, we need to keep the sign if it's negative or positive. We mostly use normal shift logic for multiplication to access arrays. Okay, so other application of logical operations is byte level manipulation. So for example, in your exam, I might ask you, for example, we have this register, please take out byte number 2 or byte number 3 of that. So if you consider bytes from 1 to 8, so imagine this is a register, and I'm asking you extract byte 2. Okay, so if you want to extract byte 2, this is x22, for example. This is byte 0, byte 1, byte 2, byte 3, byte 8. Okay, byte 2 means this part. So we want to extract that part, and we don't care about the rest. So that's one of the application, extracting. We also can do masking. Masking, if combined with shift, can be extracting. So extracting is more, you know, or aligning as well. You are just can do with shifting, you can align it, but they are all related to each other. So in this example, we have a register x22. We want to extract byte number 2. So what we need to do, normally, first we need to load this number, 0x00 FF0000. So we are extracting, but we are adding. This is kind of move, but because we don't have move, we implement move with add. For example, in X3, we are adding immediate this number. Why this number? You don't need to put even here 0 because the rest is considered 0, but I even can put 4 of this here. Doesn't matter. So the important part is this is showing byte 1, byte 0, byte 1, byte 2. This is actually showing this one because we want to mask it. We want to extract that part out. Whatever is there, the rest going to be 0. Okay, so that's what we are doing. So X3 is a mask information. Okay, now we need to AND it. We AND X3, that mask is there, with X22, that our information is there, and put the result in something else, like X2, for example. Okay, so in X2, they are all 0. Just this part passing. Good. Now what we need to do, we need to do aligning. So this is still there. We need to bring that to the least significant bit. That's called aligning. So we need to, how we do that, how we bring that to least significant part with shifting. But this time we are shifting right. Am I right? We are shifting right. So we are shifting right. Logical, how many bits? Here we need to mention bits. 2 bytes means 16 bits. 16 bits. 16 bits shifting X2 and put the result in X2. That's it. So these actions that we did, kind of extracting byte 2, so the result is going to be in X2 now, because we shift that to the least significant bit. From here, we moved it here. So if you want to draw the result of X2 after this operation, it's going to be here. The rest 0. We shift that to left, shift that to right. 16 bits. Any question about that? Good. Yeah, that's the application of these operations. So we have similar of this in C language, in Java, for example. C and Java are very similar. I don't know, in Python, is it similar notations, or I don't know. And yes, of course, and is like that, or is like that, but I don't know shift for Python. Yeah. So here, to do extraction, we kind of combining masking and aligning together. Okay, that was the takeaway of that. Okay, I clean this up. Any question before cleaning up? Clean this up. Okay. So, the point about these logical operations that they are all register based. We don't work with memory because the only instructions that working with memory are load and store. So we don't need accessing memory to do logical operations. No access memory directly. If you want to do with memory, we need to bring that inside CPU using load and then work on that. And yeah, immediate, yes. We can have immediate operations for logical, but not memory access. And as I mentioned, they are like a fundamental part of logic control and system programming. Okay, so shift operation. We already used shift operation, but here we can see the structure of shift operation, because shift operation doesn't need 12 bits, because as you remember in immediate in I format, we had 12 bits for this part. It was immediate part was 12, but we don't need to shift 12 bits. Why? Why we don't need 12 bits shift? We just use 6 bits. Yeah.
Be larger than the register.
Yeah, the register size is 64. It can't be. So with 6 bits, you can, shift left or right all the register. 64. We don't need more than that. So we consider the 6 extra part just as a function for other purposes. So in shift register, still we have register destination. The function is combining with opcode to specify the instruction. We have register 1, and immediate part is just 6 bits. You don't need the rest. Okay, so so immediate showing how many positions to shift, and shift left can be immediate or not immediate. If it's immediate, if you are shift left by I bits, it means you are multiplying by 2 power I. So if shifting 3 bits, 2 power 3 means 8. You are multiplying by 8. That's why in that example, we were shifting 3 bits. And shift right is dividing. So if you use shift right I, immediate I bits, so you're in fact dividing that number, that register, by 2 power I. So if you want to divide by 8, for example, you need to shift right 3 bits. We had that in the digital logic too, when you are multiplying or dividing using shift. Okay, so application of shift, as I mentioned, is for working with arrays. Like, for example, you have in that example, you wanted to put this in some register like x22. So if the size of register A is a double word, it means each of these elements you need to actually multiply by 8 to go between these elements. Any question? Okay. In your assignment, I think you had enough example of that. So let's have some example more about and or, and XOR. So so in this example, we are actually and these two, x11 and x10, and put the result in x9. Most of operations in RISC-V is in this way. So you have 2 operands, the operation, operand. We have 3 operands. These 2 operands, operation doing with these 2 operands, and put the result in this next operands. We don't have operands that working with memory. All operands working with registers. The only instructions that working with memory are load and store. They are important. Okay, that's important. So in this example, you can see we are ANDing these 2 registers. As you can see, we are kind of masking this. So we are let to this part move, and the rest becomes 0. Like, for example, we have 1 here, but it becomes 0. So this is called masking that we had in that example as well. when you want to extract some information out of this double word, you can use that. Extracting, for example, a byte or some bits even, you can do that. So that's the AND very example. OR is also important. OR can be used for setting. When you want to set some part of, for example, register O1, for example. You just need to OR it with a number to make that 1. In this example, we are ORing x10, whatever is in x10, with x11. As you can see, x11, this part is 1. So it's setting this part of x10 or 1. This is called setting. You are setting. It's set and reset. You're setting this time. You can reset too. Okay. Okay, that's for OR. OR duty is to set some bits 1. Okay, what about XOR? XOR, we know when we say A, XOR is like that. XOR with B is A, B bar plus A bar B. So if you XOR something with all 1, what's going to happen? So A XOR 1 is A, because B bar is 0, so this is going to be all 0, and B is 1, so it's going to be A bar. So A XOR 1 is A complement, or is not operation. So that's important too. Sometimes if you want to not do not, you can actually use XOR, for example, but you need to have X12 or X10 all 1. So this is kind of negating negating X10. So the result of this is X10 bar, or whatever notation you are using for NAR bar, like this or this. So as you can see, we are XORing these two. So XOR when they are not equal is passing. When they are equal, equal is get 0. When they are equal is get 0. As you can see, the part that are equal is 0, and the rest that is not equal is 1. So it's like a not operation. Any question about that? Okay. That's not complex by themselves, but if you sometimes wants to find applications, it can be sometimes a little complex. But other than that, it's just digital logic. It's nothing more than that. You just need to consider the size of registers and what value they're inside them, and based on application, you can play with that for manipulating registers and working with bits and bytes. I think this type of instructions are the only instructions that working with bits. The rest are working with double word or word, but this is working with bits. So numbers that coming here in this example, last example that we had, for example, when you are shifting, you need to mention the number of bits that you are shifting. Okay, that's it. This part done. Let's move to new part. We're just going to do a little talk about conditional operations. We can't finish it, but next class we can finish it. So conditional operations are when you want to make if and else. So without if and else, you can do really programming, and very important to do conditional operations. Conditional operation is changing the control flow. Control flow is each instruction after the other. But sometimes you want to jump from something to don't do it or repeat it. You can have a loop. You can have a while loop, or for loop. So let's see how we can make that. So for sure we need branch um, operation. So branch operations are, because we said we don't work with memory, for sure they need to be between two registers. You are comparing two registers. If they are equal or less, smaller or bigger, you jump to a label. What is the label? Is a program counter. You know, in your programming, you have a counter for each instruction. That's called program counter. We can see that soon. Okay, so if the condition is true, we are processing that. If not, we are going to next instruction. So normally we have these 4 groups. We have more, but the important parts are these 4. The important ones are these 4. Branch equal, branch not equal, branch less than, and branch great or equal than. Okay, so this, if I want to write the similar high level language for them, so branch equal is like, for example, you say if, okay, maybe let's see. Oh yeah, I have example next slide. Okay, let's go here. We have example. So conditional branch instruction change the program flow, as I explained. So the example, first see branch equal. So branch equal, you get 2 registers and 1 label. Label can be anything, like exit, for example, can be a label. And as I mentioned, this label is a program counter. Okay, so for example, you can have branch equal, branch equal, for example, x5, x6. If it is equal, go to less. Less is a label. Less. Okay, like that. And what you are doing in high-level language is when they are equal, you go to that address. So we also have branch not equal. So it means if they are not equal, you go to that address. For branch less than, you have BLT, branch less than, for example, x5 and x6. You go to, for example, less. I finish this one, clean this one, don't make mistake. So in this case, you are saying if x5 is smaller than x6, you go to less. And branch greater or equal x10 and x11, for example, go to down, for example. In this case, if x10 is bigger or equal to x11, go to down, for example. Down is a label. I'm going to show you in one of example to how you can write them. Any question about this? Okay, so that's for implementing if. You have 4 type of if: less than, bigger than, equal or not equal, less than, or bigger or equal. Okay, so this is example. So you want to see if I is equal to j, do g plus h, and else g minus h. So we bind these registers to these variables, and the instruction is like that. So first we are checking If it's not equal, go to else. If it's equal, go to next instruction. Next instruction, adding that. When we finish that, we need to, this is important, this is a unconditional branch because we put both actually arguments similar. X0 is always 0. We are going to exit in any case. So we are jumping from this else. Other than that, we run else and then go exit. So this is implementing a simple if in assembly language. If and else, actually. Okay, so any question about this? So I'm not going to go further. This can be next. I'm just going to show you this. I don't know if I have it. Oh, I shut down my computer. Okay, no problem. For your assignment, you use this actually simulator. Yes, so you know how to use that. What was called Venus? Maybe I can run it. Venus. Yes, it's here, the address. So to run your code, you need to come here to the editor. Oh, in this editor, it's save actually. Oh, you don't see that. Here, for example, I wrote a code. You have labels. These labels are considered like that. And then when you go to simulator, oh, yes. When you go to simulator, you can see the program counters. Those labels change to these numbers. And these codes, instead of those labels, you are considering these numbers. For example, 12 is C. Look at that. This is a program counter that you can run it. And you can see all the output in register. You don't need to show them in a screen. You can see what's going on in the registers to do that. That was actually one part of your assignments. It was extra point actually for that. Any question? Okay. So see you next class then. Next class is online class. I'm not here. I'm in Canada, and it's going to be online. Discard.